Hello, welcome back. Topic we're going to talk about decision tree as well as random forest. I'm Professor Wu, so let's get started. Now, so far we've worked a lot on classification models, right? And classification models, broadly speaking, can be broken down into parametric versus non-parametric models. With parametric models, we normally have problems and objective that looks like this, where we're resolve the model the problem in such a way that we're trying to minimize some kind of error. And once we minimize the error, we get our final objective. Similarly, for SVM, right, we're trying to minimize to find the W that minimizes some kind of objective. So these are called parametric models because we have parameters which we're trying to solve. However, besides parametric, sometimes we have non-parametric models which we are not modeling in some kind of minimization or maximization problem. With non-parametric model, the easiest one that we have done so far is k-nearest neighbors. Remember the algorithm for k-nearest neighbors, which essentially we just pick the k-nearest neighbors. We're not formulating the problem as some kind of optimization objective. Okay, so with parametric, we've learned two. With non-parametric, we're also going to learn two. The second one is called decision tree. Decision tree is one of the most popular algorithms out there right now. So you should have a general idea how it works. In order for you to understand decision trees, you need to understand entropy and conditional entropy. Okay? Entropy we have already done. With entropy, basically we're finding the average amount of information. So that's the key to remember. This is the definition of information, and this portion gives you the average. Okay? So that is entropy. Conditional entropy is the average amount of conditional probability when you average it together. So you use the joint distribution to average across two variables, right? So conditional entropy of y given x is simply the conditional probability information. Now, conditional entropy is the average information for all the possible outcome after you were told something happened. So after you were told that X happened, right? X equals some event did happen, then you're going to have the residual amount of information. So using Bayes' theorem, which is this, we can split the join into this format, and over here, x can be moved out. So therefore, we have summation of p of x, and then what's inside is just the conditional. So this right here is the conditional equation, but this one is the one that we will normally use because this is easier to do mathematically. Okay, so this right here is the equation. Now, before we move on, let's do a really quick review so that you remember what entropy is. So, given these two situations, what is the entropy? Right, calculate the entropy, and then you can get the result with Bayes two. Pause the video. The solution should be this here. Okay, you know the probability here is 9/14. 9/14. This one's 5/14. Therefore, calculating entropy should be pretty easy. Okay, now that you have reviewed the entropy idea, the next one is cross entropy. Given you have two variables, all right, x and then y. These are the two variables. Now, follow this equation. Pause the video now. Follow this equation and see if you can calculate the cross entropy. Okay, the answer for this is following this equation, right? So you just loop through each event. Probability of x has three possibilities when probability x is equal to sunny, overcast, and rainy. So when you have this, then you loop through these events. So notice all these, all the blue, are given that x is sunny. Then you calculate the conditional entropy. And if you did this correctly, you should get this result for log base 2. Okay. All right. Hopefully now you've gained some experience. Let's try this again. Calculate the conditional entropy. So this class is mostly just practicing calculating conditional entropy. Okay, pause the video. Over here is the solution. Hopefully you were able to do this correctly. All right, so we've covered the concept of entropy. Now, if you remember from the information theory lecture, entropy is basically the average amount of information of an event with multiple possible outcomes. This is what happens before something happens. So there's a way of measuring the amount of chaos in the system, right? It's based on chaos. The more chaotic the system is, the more information exists in the system, right? So randomness and chaos is essentially how you measure the average amount of information. Now, cross entropy, if you remember from previously, cross entropy is given we start with P. So we have this distribution P, right? So there's some kind of chaos involved. If we introduce yet more chaos, Q, then cross entropy is the additional chaos after the distribution Q is introduced. Therefore, you can see you start with some amount of chaos, and the cross entropy is going to give you even more chaos because you've introduced um, a, a new variable, right? Whenever there's new variable involved, you are essentially increasing the total chaos in the system. Now, conditional entropy is the opposite, right? So if you have certain amount of chaos, if X is given to you, now you know X, there's less uncertainty, right? Previously, you have a lot of uncertainty. So this is the entropy of Y is the uncertainty. That's the starting point. But once you're given X, the uncertainty should decrease, right? So therefore, this is the residual uncertainty after something is given to you. If some information, so you gain some information, and therefore the total chaos has decreased. Okay, so cross entropy is when you add more chaos. Conditional entropy is when you add more certainty, when you decrease the chaos. So after X is revealed, there's less chaos and less information in the system. Therefore, you can picture the conditional entropy as the leftover information after X is revealed, right? Maybe after X is revealed, X doesn't tell you anything. Therefore, you still have the same amount. Or if X is revealed and X is equal to Y, therefore everything is revealed, right? So therefore, because of that this relationship, the conditional entropy is always going to be equal to or less than the original amount, right? So no matter what, this is the original chaos. Once some information is given to you, this is the rest of the chaos after information is given to you. You cannot have more information after some fact is revealed to you. Okay, so this is why the conditional entropy is always less than the total. And you can imagine, due to X, right, the amount of information gained by knowing X is therefore the difference. The original entropy and the residual entropy will give you the information gain. So this is a key concept. By knowing X is giving you some information. How do you measure the amount of information that is gained through knowing X, right? The information gain is basically the original amount of information minus the residual information. Then that's the information gain. So you start off with this much information, and then after knowing X, so this is HY, after knowing X, this is the amount of information, h of y, given xf. Therefore, this portion is how much you gain due to x. And that's why it's this minus this will give you this portion. Okay? Now, symbolically, we can write it this way. Information gain is the change in information given x. And this, like I said, is called the information gain. Okay, so now we've kind of put these concepts together. Entropy measures the average chaos in a system, and the chaos increases when you essentially add more variable, and the chaos decreases when some variables are revealed to you. Okay, so chaos goes up, chaos goes down, and the difference between the chaos is information gain. If something is revealed to you, there's less chaos. The difference is the information gain. Okay, so over here we have a couple factors. This the goal here is to predict whether somebody played golf or not. So the original amount of entropy is just entropy of y, right? This is y, and then x is the entropy given outlook. So this is x and this is z. Okay, so which one give us more information about playing golf? Well, we just have to calculate the information gain given x and the information gain given z, right? So let's calculate the conditional entropy. So if we calculate the conditional entropy, I want to pause like this. I believe we did this already. We calculate the conditional entropy, and then we calculate the conditional entropy for this. Notice which one give us more information. Well, it looks to me that if this minus this is a bigger number compared to if you have find the difference between these two. So therefore, it's saying that outlook gives you more information about the final result, which is playing golf. Okay. Now we're ready to basically talk about decision tree. Now that we have really understood the concept of conditional entropy, given a historical data of whether we play golf or not, right? Based on various weather patterns, right? The decision tree algorithm generates questions based on the feature. So you pick a feature like outlook, and then the outlook split into three possible outlooks. And if it's overcast, then you will say yes, right? And then if it's raining, you will say you will pick the next question, humidity, and it keeps splitting. That's why it's a tree. So that's the general idea that once you generate this tree, you are able to take any vector and then answer these questions down the tree and finally come to a conclusion of yes or no. That's how decision trees work. At each layer of the tree, the decision tree basically pick a feature. Like at each layer, like you see how it picks a feature, and when you pick these features, the natural question arises. Well, at each layer, how do you know which features should you pick? Right? I mean, there's one, two, three, four. So there are four features here. How do we know that we should pick Outlook? Right? So what makes sense, given everything we've learned today, is that we should pick the feature that give us the most information, right? So given that we are trying to predict playing golf, which one of these X, Z, or W, which one of these will give us the most information and therefore will split the tree based on the features that give us the most information, right? So which feature should we pick first? Now, given this table that we had, we knew that the original information is this much. If that's the original information, what we do is we simply calculate the conditional entropy for every single one of them. So if we know the conditional entropy for every one of them, then we would say that, okay, we know the original minus the conditional is the information gain. So let's take the original and minus the conditional, and we'll see that this one right here, the outlook seems to give us the most amount of information. Therefore, it makes sense to start with outlook. We'll start with this question because it's then to split the tree because outlook tells us the most about the final decision, right? And then after you split the branch, let's say we split into three ways because we pick outlook, right? Having an outlook, then notice if you pick outlook, if it's overcast. So this is overcast, overcast, overcast. Notice how overcast always give you the same result. If overcast always give you the same result, then the branch leading off overcast will simply be that result. That's it. It's really simple. If that decision give you a deterministic solution, then that's your solution. However, in the case when it doesn't, For example, this branch, raining. Raining, sometimes you play golf, sometimes you don't. Therefore, what we do is we construct another table where you only have raining. And now from this table, we can once again figure out of these three which features give us the most information about the final product. Now, because this table is different from the original table, this is the original table. When you calculate the conditional entropy, it is going to be different. The conditional entropy for these three is not going to be the same conditional entropy as these three. So you do have to recalculate it. But once you recalculate it, you will essentially figure out which one gives you the most information, and you will plug that one into the next layer. Okay, so let's practice this next layer. Okay, so let's look at the raining status. This was the raining table. Identify the next feature, right? So for this practice, you want to pause the video and do it again, cross entropy, and identify the next feature that you will use. I've provided the solution here. Pause the video, and here's the solution. Hopefully, you were able to identify the next feature. Now, decision tree is a very popular algorithm. For a long time, decision tree has been one of the most popular algorithms because it's pretty easy to implement in Python, and it does a really great job, especially on simpler tasks. It also tells you which feature is most important, like which feature gives you the most information about the labels that you're predicting. In fact, it tells you the importance of the features in the order of importance. So you know which one is important, outlook. And then after that is humidity and windy, right? And you know the exact amount of information you gain from them. Therefore, you can just sort them out, right? You can sort them based on the amount of information, right? It is so knowing how to learn decision tree, it is common decision tree, right? It is commonly used a decision tree. We build further on top of it and turn a tree into a forest. So the algorithm that we are learning besides decision tree is random forest. Okay, so this requires us to learn this concept called ensemble methods. And with ensemble methods, they are be used by a tree decision. It can be used by any of your algorithms, and the ensemble method improves your results slightly. Okay, so ensemble method is a machine learning strategy that combines multiple classifiers. So far we've learned one classifier, but what if you end up using multiple to come to the same decision, right? So you can either employ them in parallel, which is called bagging, or you can employ them in serial. So one algorithm and then algorithm one, algorithm two, or you can have algorithm one, algorithm two, algorithm two. So if you go plug your value into all of them and output a result that's parallel, parallel. But if you do them in serial, then it's called um, boosting. Boosting. So serial is boosting, parallel is called bagging. Okay, so we're going to focus on bagging because that's how random forests work. So how does bagging work? Bagging works really, really easily, right? So the way it works is picture you have this data set. Now, if you were to train, take a subset of the data, and then you train a decision tree. Now you're going to call this tree one. Now, if you take a different subset and you train again, it's going to come to a slightly different conclusion because it has seen different data. Train T2. Now, if you do this again, once again, you get a different tree. So you can imagine you can keep building multiple trees, and all you and once you have multiple trees, they become a forest. So whenever you are trying to come to some kind of classification result, you simply put the data into each one of them. And then each one of them may give you a different answer. So maybe the first one will say yes. The second one will say yes. The third one will say no. And the fourth one will say yes. Right? So now you got four results. And all you have to do is take the majority vote. And therefore, this will give you yes. So basically, you are collecting many different trees and then trying to get the wisdom from the collective of the tree, which is where the forest comes in. And this right here is called a random forest. Okay. All right. So random forest implementing it from scratch is not fun, but in sklearn it's super easy. It's just basically one line of code that calls the random forest. And now you guys understand how the random forest works. Okay. And lastly, when we do classification, how do we evaluate the results? Right? When we do regression, remember we use the mean square error to essentially determine the average error. While cross entropy is the objective, very often, we don't normally use cross entropy to measure the quality of the classifier. What we normally do instead, we use this thing called the classification accuracy. And the idea is very easy. Let's look at the prediction and the truth, right? So here's the prediction and the truth. I spelled truth wrong. Truth. Anyways, in this particular case, there's only 1 out of 10 that's wrong, right? So one entry is wrong. So you will say that accuracy is 90%, right? You just take number of correct divided by total number. So this accuracy of prediction is what we normally use for classification results. And calculating accuracy with sklearn is really easy. It's just accuracy score, and that's it. That's it. So you can basically identify the accuracy number really quickly. Now, okay, for the rest of the class, I would like you to practice the idea of decision tree. Like, see if you can write your own decision tree algorithm using this table that we've worked on. Now that we basically did the first two layers together, I think these were the first two layers, you should have an idea of how to try to code this up. I did not write a code for this because I really want you guys to do it, like think through this and we will require some recursion. So, okay, so this is it for today. I will see you guys in the next lecture.